And we are on air.
All right, cool.
All right, so yeah, I've already introduced you. Do your thing.
Yeah. So I'm Aaron Taylor, and I work with a company called Meta, and we are very heavily invested in Go. Probably about more 80% or so of the code that we've written is written in Go. So I follow the language very closely because we're so kind of intertwined with it. And a lot of things in Go 1.5, which, as you may know, recently came out, were really exciting and things that I was really looking forward to. Because, as with any kind of newer language, there are a lot of kind of gotchas, things that are improving over time. And you may have read some errant blog posts about how, Go's the worst because Java performs slightly better in this one benchmark that I ran 100 times on my computer or something like that. And various little things about, how the concurrency was single-threaded, Go max proc set to 1, all that kind of stuff. Some of the garbage collection, there were some issues there with it being slow. Not much of a dependency management, but with Go 1.5, a lot of those things are pretty much cleared away. So there's some pretty exciting stuff kind of under the hood that's happened, and I'm going to be diving into it a little bit. So yeah. So first, the package system. There are two main kind of improvements that have happened. So the first is internal packages, and so this means Go has this package structure based on kind of GitHub, Git repository paths, things like that, folder structure, and previously, kind of everything at the package level that was public with a capital letter was public to anywhere. So you could import anything from anywhere. So that meant that it was nice and easy to kind of access things and very clear what you could do. But if you wanted to have neighboring packages within some piece of software that you were providing, some API, and you wanted to share code between them, it was very difficult to do because you couldn't share something private in between two packages. So with Go 1.5, you're able to have kind of an internal structure that allows for this. And I'll show a little example of that. And also, there's vendoring support. So inside of your package, you can have a vendor folder. And this is experimental, so you have to enable it with a special flag. But it's planned for kind of full release in Go 1.6. Internal was experimental in Go 1.4, and now in Go 1.5, it's kind of the default. And so if you have a directory that's /vendor, it'll look there first instead of your Go path. So you can do things that tools like GoDep and others of that ilk would do, but kind of built into the language for you without having to manipulate the Go path. So here's an example of what an internal package would look like. So we've got an internal helper package with helpme.go. And so from foo.go, you'd be able to call into that helper package, but from the bar package, you wouldn't be able to. So that kind of isolates that functionality. It's a very simple example of how that works. So we use Google App Engine a lot, and their new libraries use this kind of internal pattern very heavily. So that's an example of it. The Go standard library also makes use of this. That was one of the main motivations. In the Go standard library, there was a couple examples of functions that were shared between different packages that the Go kind of maintainers wanted to have as shared code, but weren't able to because they didn't want to make them part of the standard library. So this enables them to have reduced code duplication as well. So it's a nice thing to kind of encapsulate certain pieces of functionality if you have a nice package-oriented design within your project. A little example here of vendored packages. So if you're not familiar with the Go, Golang net context is great for HTTP requests. There's a Go blog about that. But so if our package bar and foo both use this package, this context package, bar will use the one inside the vendored folder. So that might be a different version, an older version that we've pinned to some Git hash using a GoDep or similar. And foo, if we're just, it's a hobby project or something, don't really care about the dependencies, it'll use what's in the Go path. So it provides a nice way to kind of built into the language, have structured, reliable vendor dependencies that you can keep in your Git repository or, with submodules and things like that. That's built into the language, so you don't have to go completely outside the language in order to have this kind of nice vendor predictable structure that lots of other languages provide. So those are two changes to the packaging system. Another big change to kind of the core of the language that isn't all that visible externally is to the compiler and runtime. So previously there was a lot of C code. Basically, the Go compiler was originally written in C, and that's all been translated into Go. So now there's no more C pretty much in the entire code base. So this was an automated translation process. They tinkered with the idea of doing it totally from scratch. But one thing you can provide and preserve when you have an automated translation is the correctness of the compiler. So while they translated it and it was kind of slow, it was started off 10x slower. They improved it through a lot of ways to become just only about 2 times slower for the build time, not the runtime, just the build time. It started off as pretty slow because there are a lot of things that are idiomatic in C that aren't idiomatic in Go. There's a great talk that Rob Pike gave at Gopherfest that if you're interested in this stuff, you should watch, because he talks all about these kind of edge cases, about complex for loop conditions and variable declarations and all these things that were exposed by kind of profiling and using a custom tool called Grind, just Go FMT for a lot of things, and a lot of profiling to kind of dig into what the differences were and why this is slower, and optimize it to get it up to about 2x, little less of the build time. They're going to keep on iterating on that to kind of get it back to where it was. So, but this means no more C. So it makes contributions to the standard library a lot easier. You don't have to know C in order to contribute to Go. You just have to know Go. And now the build process is totally bootstrapped from 1.4. So if you have no Go at all, you would build 1.4, and then you can compile Go with Go and bootstrap it in that way. And so before, if you've delved into kind of the lower level things of the compiler, it used to be there were all these different ones, 6A, 8A, just all these different tools for different assemblies and different kind of build targets. And now with it all translated into Go, it's much simpler. So there's just one compiler. It's Go tool compile, Go tool link. There's no more kind of separated things. And a lot of code has been reduced, duplicate code has been reduced in the Go standard library. So it makes it a lot easier to maintain and things like that. In preparation for this talk, I was looking through the standard library for some of the other things I'm going to talk about, trying to pull out some things. So it's still complicated. It's not simple, but it's much easier to approach, just knowing Go. You don't have to know the C and all the different idioms of C and design it in a different way. And so it's just it's a much nicer code base to work with for the Go maintainers. It's also enabled some new tooling to become available. There are things that are available in Go and possible in Go that aren't possible with C. C's fast and it's efficient and it's very reliable, but there are some strange optimizations that don't enable you to kind of make certain assumptions. So with the C compiler, various things, there's this new trace tool which is available in 1.5, which allows you to kind of trace through the execution of your program and see exactly what's going on. Really cool stuff. But with the C compiler, you weren't able to do that because the optimizations that the compiler would introduce, you would have to rely on undefined behavior, and it might not be correct in terms of what it was outputting. So now that everything's in Go, they know exactly what's going on, exactly what it's being translated into, and can predict and do various things, like have now a contiguous stack instead of a kind of broken up stack in terms of memory usage. And there's type safety in the compiler, so you can kind of do various checks and know what's going on rather than having void stars and things like that. So it enabled a lot of kind of tools to be developed and more reliably made that are useful to us. So trace is a really cool thing you should check out if you haven't already. Another exciting change is true parallelism. So there has been and still is in Go this thing called Go max procs, which is the number of max threads basically that Go will run on in order to have kind of true parallelism across different cores. So previously this was set to 1 because some inefficiencies with the Go routine scheduler meant that if you weren't doing things kind of that were optimized for parallelization, your program could actually end up being slower. So if you ever played with the Go max proc setting, if you spin up tons and tons of Go routines and Go 1.4 and below, oftentimes it would be slower. So, but now there's been a lot of improvements to the scheduler and the way that the scheduler does things so that it's a lot more efficient and can kind of switch between Go routines and do all the things that are necessary to have kind of multi-threaded, truly concurrent, and truly parallel programming take place in a really efficient way. So I've got a couple graphs here, which are from the some of the kind of design documents from the Go team. So this is one of the worst cases for kind of parallels. It's just totally non-parallel thing. It just basically, this is a program called Chain and Chain Buff that were just kind of benchmark programs they made. So what these do is create 100 Go routines and send a bunch of just values through each of them. So it goes one Go routine to the next with channels, just kind of to test the abilities of the language. So at the bottom here is for each of these chain and chain buff. Chain buff just uses buffer channels. So at the bottom is when there's only one channel. So in Go 1.0, 1.4, that's pretty much flatline. If you have one channel, it's not really using any of this stuff. But before, that would be a lot slower. And so that's decreased from 1.0 to 1.4, and now 1.5, it's basically the same. So this kind of worst case situation where you're really doing nothing with the Go routines, it just gets completely eliminated and optimized to be just the same. And this is nanoseconds on the side here. So another one, this is actually a pretty parallelizable program. It's a sieve of Eratosthenes. It's a way to calculate prime numbers. Very kind of old algorithm, but works really well. So the blue line here is a little tricky to kind of convert these into graphs because it's really a three-dimensional thing. But the blue line here is with just one Go max proc set to 1, and then as they go down, Go max proc is increasing. So previously, in Go 1, you can just see that trend of it really improving in quality towards Go 1.5. So parallel computation has increased as well. And here's just another worst case. This is just a power series computation, so a similar trend as the chain. Just really Go 1.5 has kind of gotten rid of all the issues with those worst case situations where you might end up with a slower program and just wonder, hey, what's going on here? Another example there. So, and there have also been garbage collector improvements. So how many people here know what mark and sweep garbage collection is, I guess? Cool, great, that's awesome. Very good. And so Go uses mark and sweep garbage collection, still uses that technique. And previously it was stop the world. So what that means is that execution of your program totally halts, and then the garbage collection happens, and then your application resumes. And those are two completely separate phases. So that has some issues because you have no real, you can trigger garbage collection, but you have no control over, or very little control over when it'll happen. It's a fairly unpredictable thing. So if you're trying to do something where, you care about this real time and things like that, the ability for your program to just stop completely what it's doing and do some internal stuff, and then you have kind of an undefined amount of time until it'll resume is bad, and prevented Go from being used in certain kind of applications where that was an issue. So in Go 1.5, that is changed, and now is a pretty much entirely concurrent operation. There are a few kind of simple stop the worlds, which are just very like a millisecond or two, but it's basically all concurrent. So your program is always executing, pretty much always executing while the garbage collection is happening, which is tricky because this application, they talk about it as this like evil mutator of state. So you have the application, which is, the wonderful garbage collector is going around just trying to keep everything clean, make sure all your memory that's no longer accessible is cleaned up and freed. But the application keeps going around changing things and kind of creating new things, and then jumping out of that scope, and then they're gone forever. And then the garbage collector has to come clean up. So if the garbage collector is, it goes through and marks everything, and then things change, you have to keep track of that, and then it has to be dealt with. So there's something called a write barrier, which basically lets the garbage collector know during this kind of concurrent garbage collection, hey, this has changed, and then it can take that into account. And as it's cleaning things up and marking things, it can take that into account and use that so that everything gets properly cleaned up and there are no memory leaks introduced or anything like that. So yeah, and then kind of one of their design goals was to get this down to less than 10 milliseconds of garbage collection. That sign might be the wrong way, but less than 10 milliseconds of garbage collection per. Yeah, that'd be an interesting goal too. But less than 10 milliseconds of garbage collection per 50 milliseconds of kind of program execution. So this was kind of their goal, and they actually got it quite below that in terms of what it'll actually do. And then to stop the world is very minimal indeed. So I was making my own slides, and then found some pretty great ones that somebody from the Go core team put together. So I'm going to borrow a few slides now from Google. So this is from a talk here. I'll link to it at the bottom. It's on the Go website. So this is a slide about the original stop the world. So basically, it's just pretty simple here. You have the application running, then garbage collection, application, garbage collection, application, garbage collection. Two very distinct kind of binary states. You have this dichotomy of kind of either it's doing garbage collection or it's running the application, no overlap. So this has the things that I was talking about before, the issues that I was talking about before. But in Go 1.5, so it's a more complicated diagram, but what you have is kind of instead of, so the blue bars indicate a stop the world, and so you have these blue vertical lines at the beginning and end of each of these phases. And so that is like a very quick stop the world, just kind of like synchronization sort of things, setting everything up. And then you have the application running and the garbage collection running at the bottom. And then in the middle, to actually get the program to assist with the garbage collection process. So the kind of typical scenario, like on a 4-core machine, would be that one of the cores, one of the threads is used for garbage collection. And then the other threads are running the application state, but then the garbage collector can request that those threads can perform some work on its behalf. So, hey, can you like delete this, free this object up, perform this kind of check or something like that. And so there's these assists that take place which help the garbage collector. So it's kind of the application is still running, ticking along, but you have the garbage collector happening efficiently. So there's no actual or very little stopped. You can see it's 1 millisecond, kind of 3 milliseconds to clean everything back up at the end of the garbage collection process. So the application is running and you have no stops in kind of the execution of no noticeable stops in the execution of the program. And what that gives you is a garbage collection benchmark, which is basically a flat line compared to what it was before. So this is heap size in gigabytes on the bottom, growing up to 25 gigabytes. And in Go 1.3 and 4, you can see it just kind of has this nice scatter plot that goes up in time. This is seconds, very large amount of time. And now in Go 1.5, it's just nothing. So there's no pauses basically at all. Which kind of open up a lot of avenues for Go to be used in new areas, exciting new areas, where before this kind of pause, this unpredictable pause, would have prevented it from being effectively used. Yeah. So this got a nice applause at Go for Con. I didn't do it. And so yeah, so just some takeaways. These are mostly internal changes. So not a lot has changed in the language itself. There's no shiny new language features, although I would love to see generics. Yeah, so I mean, Go is really improving in a way that maintains its simplicity, but doing a lot of things under the hood, and these will only be getting better. They're going to be working on better escape analysis is a thing that they talk a lot about, trying to improve the way that they detect when something needs to be moved to the heap from the stack. And just all these kind of improvements under the hood that create one of the terms they use is like a virtuous cycle. So you write this code and we have all our beautiful concurrent code using Go routines and all that. And as the language better takes advantage of hardware, more parallel, more concurrent hardware, our programs will just get faster by nature of the improvements of the compiler, not by virtue of anything that we're doing to keep iterating on the way we write our code. So it's really exciting. It's just about kind of the way the language is going. It's not breaking things and not kind of making small changes that are it's just very, very stable, and it's an exciting language to be developing it. So yeah, thank you all for listening, and there will be a blog post coming soon with lots of exciting links if you want to dig in deeper. So yeah, thank you very much.
Questions for Aaron? Sure. What's going on?
Yeah.
Do you know what the current thinking about generics is?
Don't forget to repeat the question for those.
Yeah. So the question is, do you know what the current thinking about generics is? I have looked into that a fair amount. I have seen kind of, it's always just like, oh yeah, that's an interesting idea. I don't know, maybe somebody else has seen something else, but yeah.
From our experience, it seems like it's a no, but
yeah,
they're offering generate support now.
Right. Yeah.
Prior to Go Generate existing, we had already written some stuff ourselves.
Yep.
But
yeah,
that seems to be it. They kind of want you to run Go Generate.
Yeah.
Which isn't an answer, but that's the closest we have
right
now.
Yeah, so it's like highly visible C++ templates kind of is what you get. Yeah. But yeah, so yeah, I haven't seen anything that would indicate that it's happening. Maybe, if some change happens, it would be a 2.0 thing, but I wouldn't bank on it, that's for sure. Yeah.
So the other hot button issue
yeah.
in Golang is dependency management. So how has some of the improvements sort of gotten us closer or farther away from true dependency management?
Yeah, well, I mean, it's not, you still don't have, you have your imports, so there has to be some way to kind of determine which version they are. So I don't know. GoPackage.in is a pretty cool thing. If you're not familiar with that, kind of uses GitHub releases to convert things. So one of the things they're not doing, and they explicitly said in their kind of design documents for vendor, is providing language built-in kind of dependency tools. So this is just a way for third-party tools to kind of integrate with the language more closely rather than manipulating your like kind of global application state or whatever of GoPath. To kind of have a nice way to integrate and have vendor packages. So they're not going after trying to have, what other languages provide with like a requirements.txt file or a gem file or something like that. Yeah, it's just kind of providing some tools for that to be an easier thing to do. Yeah.
Yeah, why do you enable vendoring by setting the flag to 0? That bothers me. Like second slide.
I might have copy and pasted the wrong thing. there was one where they said, there was like a thing where it said, you set it to 1 to enable it, and then go 1.6, you set it to 0 to disable it. So sorry about that. Yeah. Yeah.
Any other questions?
Sure. There's two other new features on the docket, but that I don't think they're officially part of the Go language or the Go team. That's Go mobile and Go graphics.
Yeah.
Can you say anything about what's happening there?
Yeah. Well, I mean, if you haven't seen the iOS app on the App Store that was written totally in Go, it's a calculator. It's pretty cool. I haven't worked with either of those very much. And I should say that there are tons of things. I didn't cover nearly everything in the release. So you should read through the release notes if this is something that's important to you. And just kind of check it all out, because these were just the things that interested me mostly about kind of performance stuff. But yeah, Go Mobile, I know they've got kind of increasing support for Android libraries and increasing support for iOS now as well. So that'll be really exciting to see. I don't think, I haven't seen much about people using it for kind of production applications other than the one Google put out. But yeah, I don't know. I haven't used those very much at all. I've just kind of read about them. So I can't say too much. But. Great.
Well,
thank you very much.
Bobby?
All right, I can see myself.
Sharing screen.
Nobody wants to see me because I'm not good looking. There we go. Yep. Tell Google you want to share your screen. Yes. Nice guy right there. Yeah, there we go.
That's a great Twitter handle.
Whoa. Always happens. All right. It's full screen. Yes, that is my Twitter handle.
All right, so
It's a very long story.
So, hello everybody. This is a stabby cut you. You know.
I've not actually stabbed anybody.
Yeah. Thank you. Cool. So, Sean, his real name, is going to be talking to us about some really low-level stuff. I thought was kind of cool, and it is kind of cool if you're into the low-level networking stuff. But he's also going to be touching on protocol buffers, which some of you might already be working with. So it's pretty cool stuff. So take it away, Sean.
Yeah. So as Joni said, my name is Sean Kelly. Also, as you notice, my Twitter is @StabbyCutYou. And I'm here to talk about protocol buffers and TCP and Golang, and it's a recipe for fun if you're that kind of person, which I am. I'm also going to talk a little bit about a library that I wrote that kind of wraps all this stuff up together near the end. Excuse me, near the end. Because there's a lot of boilerplate and edge cases that you run into, and so I put together some stuff that sort of wraps all that up. So the first thing is, who am I? I work for a company called Tapjoy. It's kind of a long story to explain what we do, but basically we put ads on phones. Sorry. But if you have an app that you really like and they want to charge you for microtransactions and you don't want to pay them your real money, you can watch a video or install another app or do something like that, and we will find a way to get you the coins that you want. I'm also a core maintainer of a, oh, that's a typo. My wife will point out that she should have proofread this for me. I'm a core maintainer of a couple of different libraries. One is Chore, which is Tapjoy's job system that we wrote in Ruby. We process over 100 million jobs a day in that system from SQS. There's also Dynamic, which is a queue and topic exchange that we wrote on top of React in Go. I'm actually going to be speaking about that at Recon, so if you're curious about Recon, you can check that out. And then also the library I'll be talking about a little bit, which is Buff Streams, which is streaming protocol buffers over TCP in Go. And also a whole bunch of other libraries of dubious value because I fill all of my free time with writing code for no purpose. So what am I here to actually blather on about? Well, in my opinion, the best stuff possible. Binary packed data formats, network communication protocols, streaming bytes, and of course, edge cases, edge cases, edge cases. So why do I care about this stuff, and why am I up here talking instead of someone who's actually qualified? Well, so I had an idea for a project that involved streaming and communicating between processes over TCP, and there was nothing in Go that kind of did all that for me. I wanted to stream bytes, and I wanted to use a format like protocol buffers or something fairly equivalent because it's pretty easy to use and also very efficient. But there wasn't anything that just did it all for me. But there were enough tools laying around the shed that I could basically put together my own machine if I needed to. But there was no shortage of trial and error. So there's a lot of little edge cases, a lot of little finicky bits to consider when you put the stuff together. And when you're talking about a network, nothing is reliable. So you have to basically check every single thing you do twice. So let's start with binary packed data. There's a lot of different ways you can, there's a lot of different formats for this. The one that I'm going to be talking about is protocol buffers, which is why there's a nice little asterisk there. But there's also things like Avro, which is a similar approach, but it uses a schema internally to handle the message format. There's Thrift, which is something that Facebook put out that I think Apache now sort of owns. That's more for RPC and defining procedures between services, but it's very, very similar to protocol buffers in that they both have a similar way that you define what the message looks like, and I'll cover that in a bit. It's also things like BSON and message pack, and these are just some other formats to sort of pack data down in a binary format, and I'll cover a little bit about what that means. And there's probably a bunch of others because there's just no shortage of anything in this industry. But let's talk about protocol buffers specifically, or ProtoBuffs for short, or PBuffs if you're even shorter on time. Uses what's known as an interface definition language to describe the data, and I'll touch on an example of that on an upcoming slide. It's very, very efficient to serialize and deserialize, and this is because of how it packs the data together. If you think about a format like JSON, there's no shortage of redundancy in JSON. You've got brackets, you've got colons, you've got quotes everywhere, and that's sort of wasted data when you're talking about trying to move things across the wire efficiently. And like I said, the data is represented as a very tightly packed sequence of raw bytes. So when you define a message in something like protocol buffers, you're telling the generator a lot of information that it needs to know around how it can take the data that you've given it and pack it down into as few bytes as possible, and to cram all that into one coherent message that it can then get everything back out of without wasting space for demarcators or delimiters or anything like that. So the protocol buffers interface definition languages. Most languages that you're going to want to write protocol buffers code in is going to have some kind of library to help you generate classes based off this IDL. Depending on the language, if it's something like Go, CodeGen is the way to go because Go doesn't really have a lot of dynamic facilities. Something like Ruby or JSON or Python or something like that, some of those have more dynamic or people might consider more native solutions where you don't necessarily have to do CodeGen. But behind the scenes, something is still generating code and injecting it into your runtime and whatnot. So you sort of aren't going to get around that because this stuff is a nightmare to write by hand. It also has a range of data types that it supports. Just to kind of cover this quickly, there's string, bool, raw bytes, et cetera, so forth. And of course, it wouldn't be a Google thing if there weren't 10 different ways to express an integer. You can also do custom types, which is really cool. So if you have something like a user object, and that has an ID and an email address and those kind of things, you can define that once, and you can reuse it many, many times. So it provides you a way to sort of efficiently represent repeated data structures, which is nice. So this is just a very, very simple ProtoBuffs IDL. You might notice that it looks similar, but not equivalent to how you would declare a struct in Go, and I don't think that's by accident. So if you see you declare a package, which is very similar to Go, then for that package you declare a note that will have 3 data types. There's a name, which is a string. There's a date, which is an int64 because there's no proper date time, which is sort of common in a lot of these things. And then another string for just a comment. So you could maybe think that this would be any kind of comment on a blog service or something like that, right? And also pay special attention to the fact that after each one of these, there is a number that is ever going up in sequence. That'll become important later on when I talk a little bit about versioning, but it's very important in protocol buffs where you need to make sure that each field has a unique number, and those numbers are always increasing, and that you never reuse them. So here is, based on that IDL, here is the code that the CodeGen will generate for you for a Golang project. As you can see, there's a whole lot of boilerplate. We're importing the protocol buffs library. We're importing some math stuff. We're doing some reference imports. We come up with a node struct that has a whole bunch of struct tags on it, et cetera, et cetera. Whole lot of boilerplate, basically just to get you something that you can translate across the wire and back again. I cut out some stuff just so that it would fit on the screen. That's where various getters go here. Basically, for name, date, and comment, there's a getter that gets generated as well. What's also kind of cool is there's this reset function, which basically you can just sort of use to quickly clean out a message if you so need to. I don't quite have a lot of use cases for that, but I thought it was really cool. So one question you might have is, why would you use protocol buffers, or maybe even more importantly, something just like it? Well, in a lot of places, JSON can be too slow or too large to use at certain scales. Like we covered before, JSON itself has a lot of redundant characters in it. The data format is not very big. It is very big, depending on your payload. And also in a lot of languages, it's slow. So at Taptoid, most of what we do is in Ruby. And JSON serialization in Ruby is just awful slow. It's one of the slowest things you could do. There are a couple of third-party libraries that make it faster, but it's still pretty slow. Even in Go, JSON serialization is fast, much faster than Ruby, I should say, but it's still not the fastest thing you could possibly do. Another reason why you might want to use it is because you want some kind of notion of type enforcement. So again, to compare this to JSON, who sort of becomes the whipping boy right here, there's really no way to enforce that this field should be this type. And that's actually one of the strengths of the format, because you can basically put whatever you want wherever you want, and it's up to the client to deal with it, or who's ever serializing the format, for better or worse. But for something like protocol buffers, or for messages that you might want to make sure that there's only one type, or that clients or consumers have a way to reason about what the data format under that key is, this provides a lot of those kind of facilities, and it's really, really good at that. You also want to maintain a way to do a backwards compatible serialization. So a lot of times your messages may change or evolve over time, and raw message formats don't really provide anything that help you with that. Avro, for example, is built around the notion of schemas, and so it's very good at allowing you to version. But otherwise, you would have to build your own kind of versioning facilities on top of that to publish messages in JSON with a certain schema that it adheres to, and you validate, blah, 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 and so on and so forth. But this sort of has that built in so that you know for a fact that you can always serialize a message of this type so long as it was generated with respect to the IDL. And one of the more salient ones is, quite honestly, maybe there's a service or technology that uses it that you want to use, and this is going to come up more often than you might think. This is what, they provide something like protocol buffers or Avro or Thrift, and you want to use this service. So now you have to learn how to use protocol buffers. And there's a lot of times where stuff like that comes up. So there are some gotchas with protocol buffers. One is that you can never remove fields. So if you remember, think back to where I had the fields listed 1, 2, 3. If I wanted to get rid of the date field, for example, I can't just delete it. I have to mark it as deprecated. And I can't reuse number 2, which was the sequence that it was at. The next field has to be 4. Can't reuse 2, because 2 is forever going to be known as the date field that has been deprecated. And that is so that it can handle old messages and also new ones. And this was really fun. In Golang, the protocol's codegen does not pass lint. It is code that if you have wired up to your working habit, you have golint or govet or any of that stuff automatically running whenever you save a file, it's going to annoy you every time that it tells you that your generated code looks like crap, because it does look like crap because it was generated by someone who apparently doesn't write a lot of Go. So you'll have to get used to that, at least in Go. And also, and another asterisk here because I'm going to touch on this a couple times, the message itself internally lacks any kind of proper demarcation of fields. It sort of packs the bytes in a way that it knows how to understand in conjunction with the IDL. But the message itself, the beginning and the end, also lack demarcation. It is literally just a pile of bytes that it happens to understand how to work with. There's nothing that says the message starts here and ends here. You have to provide that yourself if you want to deal with that sort of thing. So that's protocol buffers. So now moving on to TCP, which is what I sort of wanted to dig into for communicating between servers and processes. Stands for Transmission Control Protocol, and for anyone who is like really well versed in TCP, these next few slides are probably just going to be very boring for you, so I apologize. It's the overachieving brother to the User Datagram Protocol, which is UDP. TCP is very, very good at reliably delivering your data. UDP is not. TCP does this by requiring a lot of handshakes and repeated acknowledgements between the client and the server, so that if any data gets lost, it gets resent. Data comes in out of order, it gets ordered properly. And because of this, it makes a significant performance trade-off. There are some technologies that are, or I should say some protocols that are coming about that people are using to try and replace or to improve TCP. But for the time being, it's here and it is here to stay. So just some stuff about connections in general. Opening a connection in TCP is relatively slow compared to everything else that you'll do. It's also sort of expensive on the operating system, again, relatively speaking. However, maintaining an open and idle connection is actually basically free. It takes up almost no memory, and it sits there. As long as you're not writing to it, it basically sits there and does nothing. Closed connections, interestingly enough, do not actually close right away. They need to remain open they need to remain open for a brief period of time to catch any remaining bytes that the client might still be sending. So if you can imagine that you close a socket and then you immediately try to go open that and give it to somebody else, but the client doesn't know you closed it yet and they're still sending data away, that new user of your socket is going to get flooded with a bunch of bad data, and they're not going to know what to do with it. So there's a whole life cycle of how TCP sockets and connections exist and transfer between states. It's sort of outside the scope of this talk, but if you're really interested in that stuff, just go Google like TCP lifecycle or TCP connection states. If you've ever heard of half open connection or socket sitting in time wait, that's all part of the TCP lifecycle, and it's actually really, really interesting how that stuff works together. At least I think so, because this is what I call fun, and it's a really good thing to read up on if you're writing this kind of code. So the simple way to use TCP is open a connection, dump your data into it, and close it, and it couldn't be any easier than that, to be honest with you. Streaming, however, gets a little more complicated. It sounds very similar. You open a connection, but you keep it around. You don't you cache it for later reuse, either within the thread you're in or within the context of your application. If anyone here has ever worked with connection pools, this is basically sort of the idea behind that. Because as noted, opening new connections is slow and expensive, but maintaining open connections is basically free and cheap. So that's the theory that connection pools operate under. And that's a lot of the way that streaming can work, so that you keep one open connection and you just continue to reuse it. And you write data in a nearly constant stream. And nearly is the key word here, because Streaming is more of a set of behavior and not necessarily a factor of volume or throughput. You could open a connection, you could write a message, you could wait 3 seconds, you could write another message, you could wait 3 seconds, write another message. You're streaming data. Or you could open a connection and you could flood data down that tube as fast as humanly possible. Both are still considered streaming because you're reusing the same message and you're using an agreed upon format between the client and the server to handle where each message begins and ends. And then typically in a streaming situation, you would keep that connection open until basically your service ends or whatever context you're in that needs to speak over the network closes or finishes itself. So we're dealing about TCP and Golang. It's actually really, really easy to get going with. The net package is really well written and it has a lot of really good interfaces and a lot of really good documentation. If you're at all interested in writing code for the net package, you owe it to yourself to go through the Go doc and look at a lot of the examples and look at a lot of the comments in there because it's really, really well done. There's a couple of basic objects where if you're just looking to toy around with this and get going that you need to think about. One is a TCP listener. You basically just pick a port that you want to open that port, and then you'll be able to receive connections off of that socket that you can then hand off to Go routines. You'll get a TCP connection off the socket, and you basically just call read and fill buffers as fast as you possibly can. And then on the other end, you can also write outgoing bytes, and that's basically taking a buffer and dumping it into the network. And it's even easier to switch between various protocols because the netcon interface, which is how most net code is written, has a really good interface around switching between TCP, UDP, Unix sockets, and I think there may be 1 or 2 other options in there. But you can basically write the same code and use it over a number of different protocols, all by just changing the protocol that you open the connection with. And it's really, really convenient. So here's just a very, very simple TCP server code. So the comment at the top is sort of important. As soon as we enter the for loop in here, that will block the main thread, or whatever thread this is running on, I should say. So it's really, really important that you run something like this in its own Go routine. You could either do that in the start listening method, or you could call start listening method with Go. Doesn't really matter, whichever way you prefer. But basically, you would call net listen, you would pass in the TCP protocol in the port. Always check for error. If you're writing netcode and you're not checking for an error after every single thing you do that could return an error, you are doing it wrong and you're going to get into a bad state somewhere and you're going to miss problems that are ever present. As soon as you know that the socket is good and there are no errors, you enter in sort of this tight for loop here where you call socket accept. And socket accept will block. So this is where it actually starts to block. Once you've accepted a socket, check again if there's an error or not. I actually don't know what you would do in a case like this where a client connected but gave you an error. In any of the code I've written, I basically said, well, that's the client's problem. They're going to have to reopen a connection to me as soon as they're able to. I'm not going to make any assumptions about that. But otherwise, if there was no error, you basically take that connection and you hand that off to a Go routine. And why it's important to hand that one off to a Go routine as well is that as soon as you know you have a good connection, you want to get it out of the way of that socket accept, because this is what's going to allow new clients to connect. So while you're accepting one client, you can't really accept anybody else until you make it back to socket accept at the top of the for loop. So important to hand that connection off to a Go routine as soon as possible. So a couple of gotchas when you're working together with Golang and TCP. This one was a thing that I didn't realize, and so when I say you should go and read the code in or the comments in the Go doc, I mean it because I did, and I totally missed this, and I wish that I had seen it. Net has its own custom error, which includes a temporary helper, which will help you sort of reason about, is this an error that I care about, or is this an error that I can sort of just skip over for right now because it's not that big of a deal? Because those will happen. You'll definitely get 2 categories of errors when it comes to net code, especially in Go. One thing to think about is, what do you do when the client or the server abruptly kills your connection? So you're happily writing data or you're happily reading data, and that connection just, poof, goes away for any number of reasons. There's a partition, the client crashed, the server crashed, could be anything. The network is unreliable, you can't trust it. What's important to know is what to do when that happens and handling every possible place where it could happen. And that's another one that you need to watch out for, because there are a lot of places where that kind of stuff can happen depending on what you're doing, and you need to make sure that you're always prepared for it. The other thing is that for TCP itself, this is less of a Golang thing, but for TCP itself, you can tune how the OS handles it and how it treats connections. For example, the OS, vanilla Ubuntu has a very low buffer backlog, so if you have a flood of new connections coming in. You can DDoS your own box very, very easily, and I have, because you've basically opened up more connections than the OS is prepared to keep in memory while it starts opening them and working through them. There are other things you can tune, for example, the amount of time it waits for close connections, how quickly it hands those things off to other processes, but in general, you really, really want to know what you're doing if you're going to play with any of those settings, because you could very quickly get yourself in a state where you've basically hosed your ability to accurately and reliably network. So consider that those are there. Also consider not touching them unless you need to. So I want to talk about two gotchas in specific with the netcode. One is the EOF error, which is end of file. And if people here are sort of familiar with the low-level networking code, basically everything in the net package, every TCP con, every UDP, every socket, blah, 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 all of that is a net file descriptor. It's basically, which is, if you're familiar with Linux, how sockets work. They're just files on the system. And so when a socket is done sending data, it gives you an EOF. The question is, how is that actually going to manifest itself in your runtime? What do you think is going to happen? Do you think that you're going to be reading and you'll get a read of 0 bytes and an EOF error? Or do you think you'll get a read of X to the very end of the buffer, so the final X bytes, and also an EOF in that same request? Anybody want to take a guess at what you get? You cheated, but that is correct. You will get both. Both are totally normal, and they don't mean anything other than that's it. That's the end of the data. So it's not that a 0 byte plus an EOF has any kind of subtle nuance to it, although I'm sure that there must be somewhere. But in terms of your application code, they're basically synonymous. So always expect that just because you got an EOF does not mean that you didn't get any bytes on that read. The other thing to think about, another typo my wife will kill me over, is back pressure. So how does TCP tell you to calm down? Because suddenly your writes are only partially completing. And that's TCP back pressure kicking in and telling you that you're writing way too fast for it to keep up with. The TCP connection, basically every connection in Go, and in pretty sure in most languages in general, when you're writing over the network, you get a similar interface. It gives you back the number of bytes it successfully wrote for a reason. And that's because you're supposed to check that, and you're supposed to make sure that all the bytes you intended to write were actually sent across the wire. Which is the solution to the problem, is to make sure that you have checked that you have written as many bytes as you expected to, and if you haven't, keep writing that in a loop until you're done, or until the server crashes and tells you to go away, or one of the other possible errors that could happen. It's all fun and games until someone saturates the NIC, which is usually when you'll start to see TCP back pressure. And it's, under writing benchmarks and things like that, it's surprisingly easy to all of a sudden saturate a NIC, especially if your EC2 instance size is not that big. So some gotchas in general with streaming and protocol buffers. So remember, I mentioned this a couple times, they lack any kind of demarcation. So if you want to send these in a streaming fashion, you need to have a client and a server that agree upon a way to say, I know when one message ends, and I know when the next message begins. And that's one solution you can use, is to use a custom delimiter. So that would be maybe some, let's hope it's a unique sequence of bytes that says, when you see this sequence of bytes, the last message ended, and get ready to handle the new message. The drawback there is that you have to make sure that nobody puts that delimiter into a message body, because if they do, now it's going to start delimiting halfway through a message, and all reliability is lost, and you'll probably have to toss out the connection and start fresh unless you have a really intelligent way to handle that situation. The other way is to prepend a message header of, let's say, X bytes, doesn't really matter how big, but big enough, to describe the size of the resulting payload. But you're now limited to messages that are big enough to be described in that X number of bytes. So the trade-offs here are either you can use a custom delimiter, and you can risk that somebody will put a delimiter in the message and screw up your entire flow, or you can sort of put let's call it a soft to a hard cap on the message size itself, and then you can trust that I'm going to get X number of bytes. That's going to tell me how much further I need to read into the stream, and that's my whole message. So those are basically the two trade-offs you have to make here. Neither is better or worse than the other, depending on your use case. So it's all about knowing your use case and knowing which one is going to work for you. So to sort of wrap up just the general part of the talk here, protocol buffers, very, very fast, very, very efficient way to serialize data because of the binary data packing. So long as you're okay with something like an IDL and a precompile step and code that does not lint. TCP in Go is really easy to get going with, but there are a lot of edge cases and a lot of errors to handle, so you got to keep an eye on that. And using the two together is a great way to communicate between apps and services, but there's a lot of boilerplate and forethought you need to make it work smoothly. And that is where buff streams comes in. So as I said, I was working on a project sort of just on my own curiosity. I was interested in streaming and distributed systems, and so I wanted to write something that sort of had those two together, but in a very, very simple approach to it, just so that I could use it to learn. And I basically kept rewriting the same code. So I had that one project, and then I was working on something else that needed a very similar thing. So I basically just copied and pasted the code into another project. But I wasn't very happy with how it kept ending up, and I really hated the fact that I had to keep copying and pasting things. So I created a library called buff streams. And I almost called it Beamdog, and I don't know why. When I was writing it, I just kept calling it Beamdog in my head, even though that's less descriptive than buff streams, which is still a terrible name in and of itself. I think the issue is that I pictured a herd of Welsh corgis with little photovoltaic lasers on their head, beaming back and forth messages to one another. That is just an insight into how weird I am, but I did not actually call it Beamdog. So the design of this is that there is nothing whatsoever magical in this code. It is in no way, shape, or form a better TCP socket. I am not that smart. No way, shape, or form. But it does handle all the boilerplates and edge cases that you may need to write yourself or to handle yourself to stream protocol buffers or messages that look like protocol buffers over TCP. And internally, interestingly, in and of itself, it does not actually rely on protocol buffers. You could use this for anything that has that same format, which is a either a demarcated message or a message that has a size prepended to it. So buff streams actually use a solution 2, which is the prepended message size. The listener and the writer basically agree that they're going to each send and receive a message of no more than X possible bytes. Then the writer will allocate the least amount of bytes that it needs to express that size. So for example, if your message is 256 bytes, you can express that, I think, within 2 bytes is how it works. So we'll basically add those 2 bytes to the head of any message you send out and say, hey, just so you know, the following message is going to be 256 bytes or 512 or 4 bytes or whatever it is that you want. It automatically adds that to the outgoing messages, and it automatically strips it from the message prior to invoking a callback. And I'll talk a little bit about why it's a callback and not a channel. So how this works in an application. So you would define your callback for handling incoming messages, which is basically any interface that accepts an array of bytes and returns an error. Or I should say any function pointer that adheres to the interface of an array of bytes and returns an error. You would start a TCP listener from the buff streams package. You would give it that callback, and then that callback is given a whole series of bytes minus the header for you to deserialize on your own, and then to take any kind of action that you want over there. So if there is any kind of error or something like that that's on the callback that you define to handle currently. So you have to sort of be careful when you're writing your callback to make sure that it handles any error cases. One thing that I really focused on for buff streams was optimizing the performance, and this is sort of, I set an artificial benchmark of myself for that I wanted to hit 1 million messages per second over a single socket with no errors, and where I ended up was 1.1 million. So I was pretty happy with that. How did I do this? Well, I avoided all the interfaces. So as much as I really think net.con is a cool interface, interfaces in Go are slow because of the way that method dispatch works. They're not that slow, but you read a couple blog posts and you see some benchmarks and you say, well, I guess interfaces are slow, so I'm going to throw those right out. I also avoided any locking internally, and I'm going to touch on this one specifically, but I avoided any unnecessary allocations that I possibly could. So anywhere where I didn't have to allocate new memory, I didn't. And it was interesting, I'll talk about this in a future slide, but I was able to squeeze another 100,000 messages per second by simply avoiding buffer allocations. And I also avoid any kind of unnecessary state management. So the buff listener and the buff writer don't really have any state inside of themselves to manage or to clean up. And also, and this is sort of why there's a callback and no channels, I avoided channels. Channels are not fast, not for performant critical code. They use locks internally and just in general are very, very slow compared to some of the other stuff you can do in Go. And if you're clever, you can get around needing them. So for example, using a callback where a channel may have been more of an idiomatic or in some ways friendlier approach, but the callback ultimately had much better performance. So how did I optimize this to avoid allocations? So one of the things that I had to do originally,
How large were the messages?
they were 110 bytes. Yep. So how did I manage to avoid allocation? So one of the things that you do when you receive an incoming connection, the server and the client both agree that there's going to be a max possible size for the messages. So you allocate a buffer that is of that size. One thing that I initially did was that I was using a new buffer for every single message. So the client would come in, I'd read a message, go through the loop, process the message, then go back to the top of the for loop, and then allocate a new buffer. But you don't actually have to do that. You can reuse the buffer on every read, and you can use slices and some of the slice mechanics that are prevalent in Go to get around having to do that. And so basically what I did was I would read X number of bytes. So let's say there's the buffer has it's 100 bytes and I read 50 bytes. I would pass a slice from 0 to 50 into my handler, and then on the next read, I would just start over from 0 and overwrite all the old data. And if the next read only had 30 bytes, well, it didn't matter because I read from 0 to the number of bytes that I just got in. So even though there's some old stale data in that buffer, I'm basically effectively ignoring it every time I'm handling that array or really that slice of bytes into the message callback. And so by doing that, like I said, I was able to squeeze a little over an extra 100,000 messages a second just by not allocating another buffer of bytes, which you would think allocating buffers of bytes is fast, and it is unless you're trying to do it a million times a second. And so, as I said, I never used the whole buffer. I only used a slice that pointed from 0 to the number of bytes read. And so here's a little bit of a sample code here. And one of the things you'll notice is that I have a for loop here where I'm basically reading until complete, and that's to handle the TCP back pressure case. So one of the things that happened to me while I was testing this is, as soon as I got it to where I was able to saturate a NIC on an EC2 box, I started to see all kinds of crazy errors that I couldn't understand. And once I debugged it and I traced it down, I realized that my writes weren't completing. And that's how I realized that when you want to write data, you need to write until all of it's been written. But even more importantly, when you're reading data, you need to read until you've read as much as you expect to read. So in buff streams, there's sort of there's a two-phase read. First phase is to read the header. And because the client and the server both have agreed on a maximum possible size, they know how many bytes that header is, so they read up to the header. And if that doesn't complete in one pass, it keeps going until it gets the entirety of the header. But you'll see that as it keeps going through, it keeps a tally of the total bytes that it has read off of the number of bytes that it has read so far, and then continues on and then does a similar thing to get the actual body of the message based on the number that it got out of this header byte. And then at the very end, it basically passes the total from 0 to total number of bytes read into the message handler, passing that slice in, which is a pointer and not a new allocation. And so you can sort of cheat, and you can just point to a very small subset of your actual buffer array without having to allocate a new one or copy code or copy data out of that buffer, which is really nice. But buff streams does have a couple of important gotchas. One is it's not really that tested in production. I wrote this, and I've got a couple of toy projects that I've been using with it. I've got a bunch of benchmarks that I've done with it, and it seems pretty reliable from my perspective, but I'm also not writing a production system on top of it. Because you have to specify a max message, it's not necessarily good for messages of unknowable size limitations. So if you have an unbounded data set or a message size that can't really be calculated up front, it's not really good for that. It also doesn't handle serialization by design. This is up for you. Sort of cheating here because I didn't want to account for the serialization time in my own benchmarks. So I consider everything prior to that the buff streams time. Although in the 1.1 million messages a second benchmark, I do count serialization in there. It also drops a failed message on the floor. So your callback needs to handle those error cases right now. You can also choose to log those out, but there is a pretty hefty performance penalty for using log and Go. Especially if anybody here uses Logris. Logris is probably, like, I love Logris. It has an awesome interface, and it's super convenient. It is dirt slow. And even the base log package, due to the fact that it operates over interface, that sort of generic interface bracket, is really, really slow because of that, because of the method dispatch and whatnot. So log with caution in performant critical code. And generally, it's up to you to manage the TCP listeners and writers that you use in buff streams. It, by default, doesn't manage any of these for you. but there is a simple manager that I wrote that you can sort of use to get around that. It does lock internally to make sure that if you're accessing the manager in multiple threads, that there's no issues there. So the manager is thread safe, but because of that, it locks, and thus there's a performance hit. So it's all a trade-off of if you want something really easy to get going with, or if you want to manage those connections, the connection life cycles yourself. You have those options. And so that's basically it. Golang makes writing networking code really, really easy and simple, and it's a lot of fun, at least in my opinion. ProtoBuffs, again, are great for efficient format. Slices are great. Get creative with them because you can really save a lot of time and effort in the runtime itself if you use slices appropriately. And buffer streams basically aim to do all the boring parts of streaming protocol buffers over TCP. And that's it.
For your benchmarks, you said that I'm assuming that your callback was pretty much an empty callback at that point.
It was. So for the benchmark itself, actually I can show you what it was. So this is always the big mistake, isn't it? The callback itself was basically just let's see, on the server side is where the callback is. Callback basically just gets the message, deserial. Oh, sorry. Yeah, there we go. Basically just unmarshals the message if the logging is enabled, which is you can optionally enable logging. That's, again, big performance hit. Just logs it out and then just returns.
Right, so the unmarshalling step would still be 0 allocation?
No, the unmarshalling step, there are allocations in there. Yeah.
Another question would be like in the accept example that you had, like network code, you have to close the socket if you had an error?
Yes. So I can actually, if you're curious about that. So this is on the server, on the listener side?
I think it was, yeah, it was on the listener side.
Yep. So if you want to see, let's see, there's handle listen connection. So if at any point you get an error, it will, let's see. Yeah, so there are a bunch of places where I will specifically call connection closed if I know that we got into a bad state. So that's on. So when you close a connection, the server will close it, or the remote end will close it. But now you have a half open connection. So it's on you to close that and then clean up. And what will happen is at the end of this, if the connection has been closed, basically the go routine this runs in goes away, and the client will make a new connection, hopefully, and then start the whole process again.
Can that happen on accept as well?
When you're accepting, can there be an error?
Yeah.
So yeah, that was what I mentioned. You can get an error back when you accept the connection. I don't really know what the conditions are in which that would happen. I imagine there's probably plenty of them, right? But at that point, the client tried to connect and somehow failed. That's on them.
Right, so the connection is going to be nil every time when you get an error.
Actually, I don't know if that's the case or not. I don't know what state the connection will be in, but from the sample code that I saw, if you go to connect and you get an error, you don't need to explicitly close it because it's basically been broken already. That is my understanding. I could be wrong, but that is what I saw. I think somebody over here.
Yeah, you mentioned that protocol buffers doesn't delimit between fields. How does it know if an optional field was or wasn't sent then?
If an optional field was or wasn't sent, it will. So what it does, I may have misspoke a little bit. Basically ahead of every individual field, it packs a little bit of a header of bytes that tells it about what the type is and then what the size of the data after that is. And so my imagination would be, and the best thing to do if you want to know anything about protocol buffers is if you Google protocol buffers, you get their official website, which is surprisingly nice looking and actually has really, really good documentation. But basically, my understanding is that it would pack just enough information to say, there is a field here, but it doesn't have anything in it.
Okay, so it would be a similar overhead with deprecated fields always taken up.
Yeah, I would believe that's the case, yeah.
I noticed some number of close statements, but not any defers. Is there some reason did you choose not to use defer?
Yeah, so again, defer is actually, there's a little bit of a performance penalty with defer. And then also because I need to close in so many different places and where I'm closing is basically, that's it. Like as soon as in the listener code, which is what the server would be, as soon as I close, I'm returning anyway because I want that go routine out of there and I don't want this connection around anymore. I chose to just explicitly close and return because there is a little bit of a performance penalty with defer, and I wanted to avoid all that if possible.
So you're saying doing that versus doing a defer and then returning this method is faster?
A tiny, tiny, tiny bit. You would have to look real hard to find probably the performance savings, but it is a known thing that deferring something does add a little bit extra to the call stack, and there is a tiny performance hit for that.
I think the overhead was like way bigger in previous versions than it is like
In 1.5?
Yeah.
Yeah, I would also believe that. They're constantly improving the language and making a lot of these little edge cases and non-performers better and better. So I would totally believe that that's not nearly as bad as it has been in prior versions.
It evaluates the entire expression when there's a deferred statement, and if it doesn't have to evaluate anything, that's where you get the performance hits.
Anything else? One more?
You mentioned about a lot of benchmarks. I was wondering if you did anything about like JSON versus protocol buffers or any of the like serialization stuff.
I didn't do any benchmarks around which one is faster to serialize or deserialize. I sort of said at the outset of this that I wanted to use something like protocol buffers. I sort of just picked it because I thought it made a lot of sense, and I wanted to use. I knew that JSON versus protocol buffers is going to have a smaller footprint over the wire, and so when my goal was, let's see if I can hit 1 million messages a second. Well, I'm going to pick a format that uses as few bytes as possible to express what is a message.
So you didn't really evaluate message back very closely.
I did not know.
Very cool. Thanks, man.
All right, thank you.